Hi guys, welcome to the world of Physics Infinity. We have prepared themes for you to crack the JEE Main, Advanced and NEET exams. And one of the particular themes that I'm going to take on today is the concept of conductor in electrostatic equilibrium. This is one of the major concepts in electrostatics. And with this, you can handle all the tough problems that you encounter, like the distribution of charges on the plates, on the conducting spheres, on the concentric spheres, cavity in the metal, and all these problems, induced charges, etc. You will find this concept to be good. In this particular video lecture, I'll first talk about the concept conductor in electrostatic equilibrium, and then move on to discuss the distribution of charges on multi-parallel plates, conducting plates system. Well, for conductor to be in electrostatic equilibrium in electrostatics, the main reason is that a conductor is an ocean of free electrons. It's a very high free electron density, and if it is placed in an electric field, then the electrons move to the surface of the conductor in such a manner that the resultant electric field anywhere inside the conducting material, and if the conductor is hollow, then everywhere inside it becomes zero. The conductor becomes an equipotential volume. So these are various properties that we have for conductors in electrostatic equilibrium. The first, let's have a look at the major properties for this EE conductor in EE, and that is number one, the E is zero within the conductor. The electric field is zero within the conducting material, and also if the conductor is hollow, then within the conductor, within that space. Number two, there is no volume charge density within the conducting material, and also within the space if it's a hollow conductor, provided there is no charge that you place inside the space, in the hollow space. So rho, that is the volume charge density, is zero everywhere. The charge is only there on the outer surface of the conductor. Charged conductor is an equipotential surface and an equipotential volume. Obviously, if the field everywhere is zero within the conductor, then you know that electric field is a potential gradient, then potential has to be zero. Otherwise, there would be surface currents. There would be surface current and there will be volume currents, which is not possible. The conductor is not in equilibrium, then electrostatic equilibrium then. Sigma proportional to 1 by R. Well, sigma is a surface charge density, and that is proportional to 1 upon R, where R is the curvature at that region. Well, you must have encountered the action of points. If it's a pointed charge conductor, then R is nearly zero, so sigma is almost infinite, and near the conductor, the electric field is sigma upon epsilon naught n cap, so field also would become infinite. Try to remember the corona discharge and all that you learned in your learning of the pointed charge conductor. Electrostatic shielding. Oh, that's a very, very major concept that you use in many of the tough problems. The more the problems, especially that you encounter at the JEE advanced level, well, you can have a conductor and it can be a solid conductor, and there could be cavity or cavities within the conductor, and there could be charges in the cavities. There could be charges outside. So if I take a very simple situation of a hollow conductor, and there is a Q1 charge inside and Q2 outside, then what I'm trying to tell you by electrostatic shielding, that the conductor shields the outside field for the inside charge, and the field of the inside charge, the outside charge, is shielded. Well, I will have a major video lecture just on electrostatic shielding and the cavity problems and the induced charges and so on, but well, this is you are going to encounter in the discussion of such kind of problems. dF by dA equal to sigma square upon 2 epsilon naught. Another major thing, electrical stress. So every charge conductor is under stress, and the stress dF by dA is sigma square by 2 epsilon naught. So here you can see that if you go on building charge on the surface of the conductor, then the stress on it goes on increasing, and the stress is outward. You can also call it the electrical pressure. And another thing I tell you, that the electrical pressure is something like the is the potential energy density, half epsilon naught E square. We'll encounter that concept also in some of the higher problems in electrostatics. So let us now take the case of a thin, large, single conducting plate. The plate is X and it is given a free charge Q circle. I represent the free charge as Q circle. The plate is large and the face area of the plate is A. The plate area is A and the plate is thin. So the charge Q will spread uniformly on the surfaces. There are two surfaces, one circle and two circles, surface 1, surface 2, and the charge Q will spread uniformly. So Q by 2 on this side, Q by 2 on 1. This will have sigma charge density and this will also have sigma charge density, and the charge density would be Q by T 2 divided by A. Right. Now let us take the case 3 points P1, PO and P2. P2 is the right of 2, P1 is the left of the face 1 circle. So each face is going to create a field that is sigma by 2 epsilon naught. Away from it if the sigma is plus, and towards it if sigma is minus. Anyway, sigma is plus on both the sides. So E1, I have the contribution from the face 1, from the face 2, and both the contribution are to the left. I get the resultant field minus sigma upon epsilon naught I cap towards the minus x-axis, that is minus I cap. I take the point PO within the conducting material. So one surface will create the field here. This will create field to the left. So this is for the face 1, this is for the face 2, and the resultant is 0. Sure, the conductor has to be in electrostatic equilibrium. The field within the conducting material has to be 0. Now let's talk about the point 2 at P2. So for the phase 2 and phase 1, both will create a wave field that is along I cap, because this direction is I cap along x-axis. I add on together and I get the field sigma upon epsilon naught I cap. Let us now take the case of two parallel metal plates. The plates are thin once again, they are large and the separation between them is small. The face area is A. The two plates are X and Y. Plate X is given free charge Q1 and this is given free charge Q2. Now the charges will spread on the faces of the conductor on the plates in such a manner that they have to be in electrostatic equilibrium. Using Gauss's law, we can easily prove that the charges will get distributed on the faces such that on this side it is Q dash, here also it is Q dash, where Q dash is the sum of the charges divided by 2. So Q1 plus Q2 divided by 2. Whereas on the inner faces, that is phase 2 and phase 3, the charges are equal and opposite Q, where Q is difference divided by 2. I am assuming that Q1 is more than Q2. Now what is going to happen? If I consider, now both these plates right now are floating plates, isolated. I call them technically as floating plates. The switch K is open, so the plates are floating, both are, so the charges on them would remain conserved as Q1 and Q2. Right. Now if I consider points to the left of the phase 1, to the right of the phase 4, and the 2 points P2 and P4 within the conducting material, let's see what happens. At P1, you can see very well, sigma dash will create field to the left, this sigma dash will create field to the left, this sigma will create to the left, but this minus sigma will create to the right. So at P1, the field contribution from sigma and minus sigma will cancel, and the contribution from sigma dash and this sigma dash will add on to give me E dash as minus sigma dash upon epsilon naught I cap. So at P1 I have the field E1 dash, that is contribution from the phase 1, contribution from the phase 4, and that comes out to be minus sigma dash upon epsilon into I cap. Each phase is giving, of course, sigma by 2 epsilon naught. Right, now let me consider the point, let's say P3 between the plates. P3 between the plates. So once again, sigma dash will create field to the right. This sigma dash will create to the left, equal and opposite, that will cancel. So no contribution will come from this sigma dash and this sigma dash. The contributions are going to come from this sigma to the right and this minus sigma to the right, and I get sigma upon epsilon naught I cap. Well, that's the field between the plates. That is sigma upon epsilon naught into I cap, where sigma, of course, sigma, well, we can work out as Q by A. Understood? Sigma will be Q by A. Sigma dash will be Q dash by A. And Q and Q dash I've shown you here. Sum divided by 2, and that is difference divided by 2. Now let's consider a point in between the conducting material, say at P2. Now at P2, now see carefully, this sigma dash will create to the right, this sigma dash will create to the left, cancel. Look at this, this sigma will create to the left and this minus sigma will create to the right, so net field 0. Sure, within the conducting material, the field has to be 0, plate has to be in electrostatic equilibrium. The same argument goes for P4, at the point P4. Okay, now let's make things interesting by closing the switch. When the switch K is closed, then the plate Y is earthed. Now when the plate Y is earthed, then what's going to happen? What will happen to the charges on the faces of both the plates? What will happen to the intensity? What will happen to the charge density? What will happen to the potential? First point, the moment K is earthed, then the plate Y is earthed. That means the plate Y is at 0 potential. The plate Y is at 0 potential. Number 2, let's not forget the main thing, that is both the conductors will have to be in electrostatic equilibrium. Now this is the plate that is earth. So what will happen now? Let me rub off this to show you what's now going to happen. So charges from here will start moving. In fact, negative charge will start moving, because here Q dash is sum divided by 2 and all these. So whatever. Now forget about this charge. Forget about Q2. The negative charge, that is electrons, will start moving from here and will first start killing this one here. And eventually this will become 0. Now let me show you by rubbing off this and showing you after it's earthed. So this is all gone now. Well, let's forget this. Okay, let me show you now. So this is closed, so Vy becomes 0. It's an earth plate. This is an earth plate. Moreover, X and Y must be in electrostatic equilibrium. All right. So what will happen as the electrons start coming from here? First it will kill all these charges that was Q dash over here. So all this will be killed first. This will be killed, and now what will happen? It will continue to give negative charge, till this point over here, the field is 0. The field is the vector sum of the field of this plate. Now this plate has two surfaces. So what will happen? All the charge that is Q1 should come over here. So this plate should become minus Q1 and the density here should be minus sigma 1. Now you'll ask me why. If this is minus Q1 here, then by Gauss's law, this whole charge should become Q1. So this also will become 0. So charge here will become 0. Charge here will become 0. Charge here is Q1 and this is minus Q1. Now let us check why this will be so. If I take this point P4 here, then this will become sigma 1, where sigma 1 is Q1 by A. Sigma 1 will be Q1 by A. Now let's check over here. Sigma 1 creates a repulsive field here. Okay, sigma 1 by 2 epsilon naught I cap. And minus sigma 1 will create here. Equal and opposite, that should cancel to give you 0 here. So the plate Y is in electrostatic equilibrium. Now, let us consider the point P2. So this will take later. So let's take the point P2. Sigma 1 will create repulsive field like this, and minus sigma 1 here, equal and opposite. So again the field is 0 here. Now a student may think, obviously can think, that suppose a part of Q1 is here and a part of Q1 is here. Well, once this happens, then field here is 0, field here is 0, and the field now only is here, and this P3 will now become E1 arrow. So E1 arrow is between plates, in the region between the plates, and that will be sigma 1 by 2 epsilon naught, the contribution of the phase 2 and the contribution of the phase 3, that is plus sigma 1 by 2 epsilon naught I cap, and that becomes sigma 1 by epsilon naught I cap. Okay, now I come to that question. Suppose a part of Q1, suppose some positive charge is here and some positive charge is here. Then what will happen? Well, then you can't have the field here 0. Because some charge here will create a field like this, some charge here, okay, maybe a part of this will create here, and this will create here. So that is violated. Electrostatic equilibrium is violated. Another thing, why the whole of Q1 will come here? Check it now. If this Q1 is here, then I've already shown you this surface will have sigma 1, and by Gauss's law, this will have minus sigma 1, minus Q1. So the field is coming out to be 0. Sigma 1 creates a field to the right, minus sigma 1 to the left, and it cancels. So this is what will happen when the plate Y is earth. Now I ask you a question. In closing the switch, how much charge flows down to earth? In closing the switch, how much charge flows down to earth? Of course, the answer. Originally it had Q2, and finally it had minus Q1. Originally it had Q2, and finally it has minus Q1. So the charge that will flow down to earth via this switch will be Q2 minus Q1. That will become Q2 plus Q1. Another wonderful concept, that if you earth the plate, then the total charge originally on the floating plates, originally the charge was Q1 plus Q2. So all of that goes down to earth. Well, that's what we say, that the positive charge goes down to earth. Positive charge never moves. It is actually the electrons that go. So the negative charge moves from here and the final charge here is minus Q1. So this helps you in understanding what happens when one of the plates is earth. I'll take up this later on when I'm loading a video lecture on capacitors and energy conservation. Then a lot again I'll discuss in case of discuss about the energy conservation for the capacitor, CR circuit and so on. We'll now push on to the case of 3 plates. Okay guys, now we move on to the interesting situation of 3 parallel conducting plates, X, Y and Z, parallel to each other. The distance between X and Y is D, and between Y and Z is 2D. I give free charges, Q to this, 2Q to Y and 5Q to this. I apply 2 switches, K1 between Y and earth and K2 between X and Z. Initially, my question is now, what will happen, how much charge will flow to earth when K1 and K2 are closed? So first let us take the case, what are the charges initially in the case 1 when both the switches K1 and K2 are open? Easy. For conductors to be in electrostatic equilibrium, we have done that earlier. Outermost faces will have sum divided by 2. 5 plus 2 7 plus 1 8. So 4Q here, 4Q here. If this is 4Q, it should be Q here because total should be 5Q. If this is Q, this should be minus Q. If this is minus Q here, it should be 3Q here because total should be 2Q. If this is 3Q, by Gauss's law, this should be minus 3Q here. 4Q is already here. Ye dekh lo, 4Q minus 3Q gives you Q. Perfect. You can also check that by these charge distribution on the faces, every plate, every conductor is in electrostatic equilibrium. How? Suppose I take a point here within the plate Y. 4Q creates field here. This 4Q creates here. Cancel. This 4Q creates here. This minus 4Q attractive creates here. Cancel. This minus 2Q attractive here. This 2Q repulsive here. Cancel. And like that, you can check it, a point here or a point here, they will come out to be in equilibrium. The fields would be 0 within the conducting material of all the plates. Fine. Now I close the switch, K1 and K2 is closed. So let me close it. I close this. I close this. When the switches are closed, K1 and K2, then plate Y is earth and plate X is connected to plate Z. So Vy is 0, it's an earth plate, same potential as earth, and Q plus 5Q will be divided on the plate X and Z. But very interesting thing now, the moment this is earth, the outermost faces will have 0 charge. Now this you remember always, like I explained to you in the case of 2 plates. If any of the plates is earth, any of the plate, I could have given you plate Z is earth or plate X is earth, any of the plates is earth, then the outermost faces will have 0. So this will become 0, this will become 0. That's over. But the problem now is these two are not floating plates. They are connected and the total charge is 6Q. So how do I divide the 6Q on this and this? Very easy. I give you a simple clue. This distance is 2D, this distance is D. Epsilon naught A by D. Think of the capacitance. So the capacitance between these 2 plates is twice the capacitance between these 2 plates. So of the 6Q, this will have 4Q and this will have 2Q. Because the capacitance here is twice the capacitance of these 2 plates. So this will have 4Q and this will have 2Q. If this is 4Q, by Gauss's law, this should be minus 4Q. So 3Q becomes minus 4Q. If this is 2Q, by Gauss's law, this should be minus 2Q. So you have the charges 0, 4Q, minus 4Q, minus 2Q, 2Q. And look at that, 2Q and 4Q conserved 6Q because total on X and Z should be 6Q. Now the question, how much charge has gone down to earth? Very easy now. Originally this plate had 2Q and after the switches are closed, this had minus 6Q, minus 4Q, minus 2Q, 6Q. So 2Q minus 6Q, that is 8Q. That's the answer. So like this, through this video lecture, I've been able to explain to you the concept of the electrostatic equilibrium. You see how important it is, and this will now be used to many higher conceptual problems. I'll be producing many more video lectures for you one by one now on, I have themes on every chapter, in every section I have important themes for the IIT JEE and for the NEET entrance. So if you like my video, if you like this video, give a thumbs up and subscribe so that it encourages me to give more and more videos to you. If you want to have any comment, you have any doubt, feel free. I'll answer you, whatever your doubt. Thank you.
If you love the video and want me to make more useful videos for you, subscribe my channel and hit the bell icon to stay updated.